So this is 9-4. We're doing the alpha lesson today, but we're starting this with the AP, the end of the AP video on Lagrange error bound.
And for the maximum value, unless there's an amplitude to multiply it by. And then sometimes, case 3, my favorite case, they just tell you the maximum value. They just say, this is the maximum value. That would be pretty nice, wouldn't it? And then they just tell you that directly or indirectly, and you just plug that number in to do it. So let's take a look at a quick example here. So here's an example. Notice this is a graph of the fourth derivative of the absolute value, and it says the function f has derivatives of all orders, and let p sub n be a nth degree polynomial centered where? At 1. So our center is at 1. Let's show that f of 1/2 minus the third degree polynomial at 1/2, the difference between those two values is less than 1/12. This is how you might see error questions asked quite often. It has this sort of f minus the polynomial absolute value. We know it's an error question, and so we have this idea of our Taylor or Lagrange error bound, right? And so we know that number 1, our degree is 3. We also know that the center of our polynomial is going to be 1 according to this. And we know that we're doing this at the value of 1/2. So our x value here is going to be 1/2 based off of this. And so if I go through this process, I know that the remainder, the Lagrange remainder here, is going to be bounded by the absolute value of 1/2 minus 1, x minus c, to the n plus 1 power, meaning if I'm doing a third degree, I got to use the next term, which would have been the fourth degree, over n plus 1, or 4 factorial, and then times, and this is that important part, the maximum possible derivative value of the fourth derivative, right? The fourth derivative, what's the highest possible derivative anywhere between the center and the value that you're approximating? Well, here's our center, c, and then we're approximating at 1/2, and so we're saying between these two values, what's the highest maximum possible derivative value? And between here and here, we can see that the maximum at the fourth derivative, but on the interval, is right here. That's going to be the maximum value. Whatever that is right there, that's the maximum. And this is when I say we kind of overestimate it, because we don't know exactly what that value is. We can tell it's a little bit less than 30 and more than 20. And when that happens on a graph, don't try to predict it exactly, because you can definitely be wrong and end up losing points. Just pick the higher value, be safe, right? I'm 100% sure it's definitely not more than 30. So I'm going to use 30 for that value. I'm just going to use 30 for that value. And then if we're able to just simplify this a little bit, we're going to get 1/2 to the fourth power on the top, and then 4 factorial is going to be 24 on the denominator, and then times 30. And doing a little bit of arithmetic, we're going to get 1 over 16 times 24 times 30. 1/2 to the fourth power is called 2 to the fourth power in the denominator. And then reducing this a little bit, it's going to be a number, right? I'm going to do this by hand because I like doing some arithmetic. 30 becomes 15, 6 can reduce to 8, and then I can reduce the 15 divided by 3, and that becomes another 8, and I end up getting 5 over 64. And so I know that the remainder, the worst case scenario based on this, is that the error has to be less than or equal to 5 over 64, and guess what? 5 over 64 is less than 1/12. And so we just showed that the error from Lagrange is certainly less than 1/12. So when you're doing a problem in the AP exam, it's important that you show them the formula you're going to be using in Lagrange form, and then show them that you connected your answer when you were done to what they wanted you to compare. They said show it's less than 1/12. Don't just say it's 5 over 64. Show that that value that you came up with, the worst case scenario, is less than the value that they wanted. Thank you so much for joining us, and good luck to you this year, and we'll see you next time.
So we're going to continue and go over the beginning of the PowerPoint for 9-4. Okay, so we have to understand the distinction. What does it mean to say the series converges? And does this series converge? Can you think of this in context of the H chart? So if the numbers in the H chart in the middle column, so I've got n, t sub n, and the sum. If these numbers are getting smaller, then the sum is slowing down. But that doesn't guarantee that it converges. So if something would go on and on without bound and go to a number, then it converges. But the first thing is those numbers have to, in the middle column, have to be getting small. So this is the dopiest thing I've ever seen. The nth term test for divergence. And it's confusing because what does it mean? It just says if the terms in the middle column, the H chart, are getting bigger, then the series can't possibly converge. So it's a test for divergence. Okay? Something diverges is not helpful to us. It can prove that a series diverges, but it doesn't help with the convergence. So what's happening here? So if you have n factorial times x to the n, we get, okay, start at the 0 terms. I put 0 in here. 0 factorial is 1, x to the first is 1, x to the 0 is 1, to the sum is 1. Yes? And I put 1 in here. So I would have 1 factorial times. Oh, so not 1, I get an x. 1 factorial is 1 times x to the first gives you an x, so you have 2x. Is your sum. You see what's going on with the H chart? You're either adding straight down or you're adding diagonal. Put 2 in there. 2 factorial is 2x squared. Okay? This thing is diverging. The numbers are getting, it's just growing. So it's not going to, it's helpful. We just kick it to the curb. Now, how did they do this? They looked at limits and said, oh, well, I can rewrite this as n factorial times the reciprocal of 1 over x in the denominator. So if you do that, you have 1 over x as n gets larger without bound. So what's happening to that? Your numerator is getting larger, and your denominator is 1 over x times this, times this, times this, times itself. Right? And then when you invert and multiply, the x would come up here and the thing getting larger without bound. So the nth term test is really not helpful. It's just telling you what you would know by common sense. If the middle term in the H chart is getting larger, then the series is not converging. Well, that's what we're trying to do. This is the big thing we're trying to do. What is the interval of convergence? And the endpoints. The endpoints are 9, 5. We're not worried about the endpoints yet. So we have an interval of convergence and the radius. Looks like anything else. The radius is half the width of the interval. So here's what we're doing today. Today we're just doing the direct comparison test as far as we go. Now, this is very visual. Ready? If you know that the red series, you don't know this, but if they tell you the red series converges, then the blue series has to converge because it's above the red series is above the blue one. So if you compare it to something you already know converges and you're less than that, then it has to converge. If the red series diverged and the blue one's above it, then the blue one must diverge. This is all common sense, but it's very visual. It's very helpful with that picture. So how about this example? Prove. And people get intimidated by the word prove. Prove is your friend. Well, I don't like to do proofs. Prove is your friend because they're telling you this thing converges. They just want you to do the work to show it's true. The harder directions in math, simplify. Or if it says doesn't converge, well, that's harder. They're saying prove it converges. So here's what you got. First thing, we have a separate category for alternating series. It's actually easier. So these terms must all be positive for direct comparison. Now, do you understand what happened there? The numerator is property of exponents. The denominator, they're saying, what I'm given, this denominator is larger than just n factorial. So therefore, this thing has to be less than or equal to the way they wrote it. Well, why did they get rid of the exponent? Because it's direct comparison. You're going to compare it to something you know. Meaning, oh, that's e to the x, where you substitute x squared for x. How would I know that? God bless you. You have no choice. Ready? You are accountable for, and it's on the PDF. You're accountable for sine and cosine, e to the x, in the geometric series 1 over 1 take away x. They're the only ones you would use for direct comparison. All right, so this is what we'll start with tomorrow for the beta lesson. PDF. First thing is you're going to read question 58. What is the radius of convergence for this series? Okay, we can't do this yet. We just want you to read the question. But you have to understand something. In order to answer this question, you would find the interval of convergence, and the radius would be half the width of the interval. So as long as you understand what you're looking at and how to do it, we're fine. Because what you saw on the AP Classroom video was from 9.3, and what we showed you on the PowerPoint this morning is not enough to answer that question. So here's problem 29 in the book. And it says, ready? This is an nth term test for divergence, which is not helpful. So it says, suppose you have this. First term is 1. If I put 1 in there, I get 1/2. I put 2 in there, I get 2/3. The middle column of the H chart's getting bigger. So by the nth term test, this thing has to diverge. This is a silly question. Okay, I just wanted to show you what it would look like. So, convergence, direct comparison if you have no negative terms. The ratio test is the bigger deal. That's what we will do tomorrow. And that's how you would solve problem 58 that we showed you to start with. Now, this is what was not on the PowerPoint. It's the same problem, but they didn't show you, take you through the work. So I'm telling you, e to the x is the only non-geometric, the tilde means not geometric series you're accountable for that has no negative terms. We can't use sine and cosine for the comparison test because they include negative terms. So the only thing you could possibly use for direct comparison that you are accountable for is e to the x. That's why it's important that you know the expansion of e to the x. So this top line is what? That's what was on the PowerPoint. What does that look like? Well, starting at 0, I have 0 factorial x squared raised to the 0 plus 1 factorial x squared raised to the first, and so on. That gives you a 1. That gives you x squared over 1. That's x to the 4th over 2 factorial, which is 2. So this thing right here is the expansion of e to the x, where you substituted an x squared for x. And this thing that we started with has a larger denominator. So it's like the picture in the PowerPoint. If we know that e to the x converges, and this question is less than it, then it necessarily converges. Okay? And then I'm showing you here, go to page 491 of your book, and if you look on page 491 of the textbook, those are there's a table on what you're accountable for. That gives you sine, cosine, and e to the x. It gives you some other ones which you don't really care as much about. 1 over 1 take away x is kind of like, no offense, but that's easy. The other ones, sine, cosine, and e to the x, you're accountable for. So what's up here, which what's on the PowerPoint, is your model. We're going to pause this and send you to problem number 3. So this is pretty transparent. Why? Because there's only one thing you're accountable for if they ask you direct comparison. So it's the same question with different terms. It's what? It's x to the 3n. You're just replacing the 2 with a 3. So that's e to the x, where x has been replaced by x to the 3rd. And the series they gave you, when you look at the denominator, it's 2n factorial plus 1. That's really confusing. All you need to know is 2n plus 1, 2n factorial plus 1 is bigger than n factorial. So if the given series has a bigger denominator, then it has to be less than what you know, which is e to the x. So that's how that was done. Okay? Now,